Okay, so we're gonna follow through from all this admin stuff and intro with actually what is computer architecture, right? What do we do? So I'll motivate it by showing this. Right? Anyone been there or even know what this place is? By the way, this is like a really, really good side effects from going to a conference. So this is basically I had a chance to go. Yeah, it's the Louvre Pyramid in France, in Paris. So it just happened that in 2000, I think 14, I had a chance to go to a conference in Paris, France. And it was pretty nice because, to be honest, I went to the conference, give a talk, and then in the evening we just walk around, right? So I took this picture, and the reason why I basically bring it up here is uh to design such thing, right? What do you need? You need an architect, right? And you might have noticed that, I mean, the two words has some similarity: computer architecture and an actual architect, right? What's the difference? So if you look at the job of the architect, what's the job of the architect? For example, in this case, like this is an architecture masterpiece by I.M. Pei, right? You walk around in Paris. Like, to be honest, I did not look up when I was walking in Paris at that night, right? I didn't even look up where's the Louvre because I didn't have a lot of time. I just walk around and say, hey, what around. I'm just explore the area nearby the conference venue, right? And then I stumble upon this. My first thought was like, what? Right? Because the thing is, if you walk in Paris, right, the Parisian street will have a lot of like old buildings and uh like really, really nice looking European style building. And you saw a pyramid. What what are you gonna think, right? So it actually caught your eyes. And you think about it, right? My internal interpretation might not be the same interpretation of the designer, but pyramid also kind of suggests that this is like something that has to do with the history, right? With archaeology and art and every like how human uh of the old days start building things, right? And this is basically just the entrance to the Louvre Museum. If you want to go in, you actually go in there and walk down. Oh, not walk. That's an escalator down to the main floor. Everything is underground, right? And the reason why they're underground, uh, it actually helps with the uh, uh, protecting the art pieces and all these cultural artifacts from the environment, right? It does have the usefulness in putting things underground actually make it hopefully easier to keep all these artifacts and piece of arts, right? So that's one example of a really, really good piece of architecture that you can see around, right? So let me imagine, I'll go through, let you go to another journey. This is a picture. This place called Cucumber Fall is actually nearby Pittsburgh, which is close to Carnegie Mellon and CMU. And then if you drive out of Pittsburgh for about an hour, I think, you'll reach this kind of it's a state park called Ohio Pile. In there, there's an area called Cucumber Fall. And the reason why I take this picture because it's actually really, really photogenic. It's like it's a small waterfall enough that you can capture in a frame, right? But at the same area, right, there's this building that's built by, well, is owned by a rich family. So let's say I have a lot of money and say, hey, I want to build a house on the waterfall. And I take the idea to an architect. And this is what you get. So again, in a really, really close by area inside Ohio as well, right? The same state park in Pennsylvania. You will see this structure. It's a house. It's called the Falling Water, which is currently a UNESCO World Heritage Site. This is the house built by Frank Lloyd Wright. So if you know or study architect, you will heard about both of the names. To be honest, I.M. Pei and Frank Lloyd Wright. They are prominent architects in their time that designed a lot of buildings across, like all over the world, to be honest. And as you can see here, it does serve a purpose as well, right? And now my cat is trying to steal my water. What I do is steal it first. And now he's drinking. Unrelated to this lecture at all whatsoever. It's just my cat is right here. But with this, right, my problem is I want the house next or actually above waterfall. And that's a really hard problem to solve, to be honest, because if you want to build a house next to the waterfall, you need to think about how do I make sure the house stay and functional, right? And how do I take advantage of the fact that there's a waterfall right nearby, right? So the way they have this, they have the balcony, as you can see here, right, in this area, that kind of overlook the waterfall. So when you go to this museum and you walk on the balcony, you can see like basically the whole thing opens up to like a really nice like waterfall followed by a stream of river, right? So if you have guests coming in, they can see that. And then inside the building, they also design it in such a way that it forces everyone to come out and enjoy nature. So the bedrooms will be kind of small, the living area is kind of small, but the area where you hang out, like the balcony, to be honest, the living room is actually big. So the architect kind of designed, everything has an intention. Everything has a reason behind the design, right? So the same thing goes with computer architect. Everything we try to build in to a ship, the way we design it too, basically it's kind of trying to answer what are we trying to achieve, right? There's a goal and we design something based on the goal. What we do is we design, instead of designing buildings and house and like what goes into the interior of the house, we design the computer. And I stress on the word design. We do not come up with like say the material. Those are for the material science expert. We do not come up with the circuitry, the internal circuitry that goes into like the transistor. Those are for circuit people. We design and put together components to make your computer function. All right. It should to actually do it well, you need to kind of fundamentally understand the circuits and the software, and hopefully you know the user demand. And to evaluate design, usually we look at multiple things, including performance. How fast is my chip? Functionality, can I use it for a bunch of program, or does it run on certain program? Or how easy it is to use my chip? Cost, do I have to pay a lot of money? Usability, who can use my chip? Is it useful? Can I use them? Etc. Things like power, right? If you want to design a good mobile chip, right? You know that mobile phone has a battery attached to them. Battery means that I have only so much peak power that I can deliver. If I use more power than that, my battery is not enough to satisfy that, and the whole thing would crash. So the way you design a mobile phone chip is you have to now have also power constraint. I cannot go over this many watts. That's my cat. All right, give me like 5 seconds. I'll take it out of the room. It's like climbing everywhere. Sorry, he was climbing on the top of my bookshelf and pulling something down. So at least those are not breakable. And there's always key goals in designing a good computer. So our job is to identify and achieve them. And the role of an architect, this is basically adapt from Yale Pat's lecture. Yale Pat is my advisor. So his owner Mutlu's advisor at UT Austin. He's one of the prominent architects of our time. So he said, hey, we should be able to look backward, right? If you look at old codes and examine them, you should be able to analyze and evaluate previous proposal. What are the trade-offs? What are the good stuff? What's the bad stuff? So you know that if you want to deliver something, what would be the design that makes sense that we had before? Look forward, listen to dreamers, talk to people who need new hardware. That way you know the demand of new application and then to push the state-of-the-art design. I'll give you a few examples. For example, machine learning, right? This workload that we all know and love right now is one of the hot topics these days. If you listen closely to the software developers and also people who invent machine learning algorithm, you will know that, hey, there are certain operations that are more common than others. Things like vector matrix multiply is used a lot. There are certain things that's used a lot, so maybe we can design hardware for them, right? This allows you to push the state-of-the-art design further into the next generation. Look up, know the nature of the problem. Look up means up the compute stack. Compute stack start from algorithm all the way down to circuit. So as a kind of like the middle guy between the hardware world and the software world, you need to know the software. So you know what's their constraint, what's their assumption that we can make to make a better hardware. And then you should look down the stack as well to the circuit and the material science to know, hey, what are the possible future technology that we can use in the next 5 years, in the next 10 years. This allows you to predict what's going to become the future technology. All right. And here's the compute. This is the, I don't want to use this word, but this is the truth. This is what make Thailand CS and computer engineering community so shitty. By shitty, I mean it's really bad. Because for most of the Thai people and developers, right, what they understand is, I just want to write a program for X and Y and Z. What do I need for that? Front end, some web application or some non-web application or some mobile application that's backed by a backend, which basically you go and work with system configuration, make it run on the cloud, and then everything else is black magic. Everything else underneath is becoming a black magic. And here's the truth, right? When you break down the problem from your client, from your customer, basically you have a lot of things involved. You have the algorithm. You should not always replace a good algorithm design with some library all the time. Sometimes maybe you want to write your own, right, to be more efficient. You then write a program. The program will get compiled by a compiler. Fun fact, a lot of major tech company has their own compiler as an internal compiler to optimize their code. Runtime system, the ISA and microarchitecture, the green part is what we're going to focus on for this class, right? And then down there, there's logic, there's device electron. If you graduate from the undergraduate degree in Thailand and you've been working for let's say 4 or 5 years, you must be starting to question, why do I learn things like logic design or why do I learn things like compiler? The truth is, if you work in a real tech company, those topics are actually getting used, right? So this is what I want you to get across here. These are things that you need to know. These are things as an hopefully expert in your area, you should know that at least they exist. So that you can know if you have to consult certain things, you know where to explore, where's the solution. All right. And then the design choice that you put in affects software programmer because you are right in the middle here, right? everything I do in the hardware is going to affect programmer. So a good design will make sure that it kind of minimizes the programmer effort. For example, if I buy a new chip, maybe I don't have to rewrite a program. That's perfect, right? And the architecture and system kind of link the gate and wires to the computer code. So that way the programmer doesn't have to worry about how do I wire these things up? How do I link all this code up to my circuit, right? And this is kind of basically the power of abstraction, to be honest, right? As a user, the more abstraction lead to more productivity. You buy a computer, it works from the get-go. You buy a computer that comes with Microsoft Windows or Linux or Mac OS. The OS, the operating system, hides away the hardware. You got the hardware with that specification. You did not have to program and have to worry about hardware at the same time. That's the power of abstraction. You assume that things work. The OS makes sure that things work. Okay, and that's really awesome. The thing is, at the same time, you might be asking, then why am I in this class, right? So the thing is, you might want to know things like, okay, if I run on my computer, how does my program actually get run? So if I want to optimize them further or want to redesign certain parts of your program, if I know how computer run, maybe you can evaluate, is it worth it to reprogram or to rewrite certain parts of your code, how to optimize your code, right? And again, with the abstraction, you can re-optimize your code without hopefully going to assembly or the machine code, right? You can just rewrite your function in Java or C++ or Python that are more hardware friendly, and then hopefully by some hardware magic, it runs faster, right? But in reality, at the end of the day, each transistor that you have on the chip are being kind of controlled automatically by the hardware, right? So the question of why should you care is, to be honest, here is, let's say your code is slow, it does consume a lot of energy, so you switch to your new computer, which by definition new, it should run faster, but when you run your program, it should run slower. What happened? Your program produced incorrect results. You run into seg faults, or you use C and C++. This is like your nightmare, right? Your code may computer hangs. Your code shuts down a computer. For example, I can write a micro benchmark that run on a GPU, and then if I do certain thing, the whole cluster shut off. I mean, I can try that, right? Knowing how computer really works will help here, right? Because it kind of gives you more understanding into the question of what happened to my code? Why doesn't it run, right? And from program to binaries, basically, let's say you write a program. This is like a program in C, C++, to be honest. This is a source code. One thing you notice, right, is how many programming languages are in the world right now? A lot, right? Can someone give me, each of you, there are 5 of you here, can you give me one language? Just type on the chat. One programming language. So hopefully we have at least 5 of them. Right? JavaScript, I'm not sure I would call that a language, but let's say Java, all right? Go, C++, Python, C#. I like the choice of like, hey, someone use C++ or use C#. One quick note here is I don't think we actually use a lot of functional programming here. So if you heard of Scala or Rust or Haskell, assembly, I'll leave assembly as a different thing. Assembly is more of the machine language. Well, not machine language. It doesn't. My intention is I don't want to include assembly. Yeah, someone has nightmare. It seems like when I brought up Haskell, it's like. Tell me more. Tell me more. We have time. What happened to Haskell? Oh, I just love it. Quote unquote. All right, ladder. Never used it before. Kotlin. Heard a lot about that language. Never tried. Should learn at some point. To be honest, for me, recursive nightmare. Yes, functional programming. Basically, recursion is like a nature in functional programming. It's a flavor that a lot of people love. A lot of people do not love. Personally, when I learned it for the first time, I was like, hell, it's too much. These days, it's getting better. You can get used to it. To be honest. Also, that's not a language. HTML is this different. So from our example already, you see that there's so many different languages. It run on the same computer. How come? I mean, think about it this way. What is the spoken language on your laptop? If you want to talk to your computer directly, what is binary? Binary also implements using some kind of ISA. Some of them can be x86. Have you heard of x86? So if you use Intel chip, AMD chip, that's a really good shot that you're using x86. ARM, if you buy the Apple M1 and M2 chip, those chip talks in ARM ISA. There are also a lot of upcoming RISC-V chip that basically talk RISC-V. And here's the thing. If I have an x86 chip and an ARM chip, can I have them talk? I mean, without any support. Okay, let you guys talk. I cannot, right? They talk different languages. The binary used in x86, the same exact binary, 101111, whatever pattern, the same exact binary that are runnable on x86 will not run on ARM. Here's my point. But let's say you write a program in C++. So let's say you write a program in C++. Can I make it run on my x86 computer and also ARM computer? If I have a source code. All right, long, awkward pause. I saw someone typing in this. No one typing. But okay, quick, think about it this way, right? I can use the same binary file on every single, well, I mean, to be honest, the same pattern, right? On the same x86 machine. But the same file, if I try to run it on a ARM machine, it will not work, right? But if I have a C++ or Python code, I can make it run on my x86 machine, and the same code will run on the ARM machine. What is the intermediate step before from your program to the assembly? Compiler, yes, thank you. Yes, that's the middle layer between the structure of the programming language. There's some entity that kind of compile and translate into machine language in assembly that are executable, right? So if you think about it, right, from this example alone, right, I can design a new language here. Let's say I have a new language. And I want to make it run on the new hardware. I just need to then what? Build a compiler, right? Then you build a compiler. And make sure the compiler compile into the assembly that is compatible with the hardware. This allows you to decouple programming language from the machine side, which is assembly. As long as it can have a compiler in the middle and you can translate whatever you do in a programming language into the binary for that chip, we're good. This also, so I was talking about the software development part, right? I can do whatever I want with the software now. As long as I have a compiler, it will run. Yay, right? Same thing. I can now do whatever I want with the hardware. If I don't change the assembly language, but I change the internal, so I make the internal hardware different, but use the same assembly language, it will work. So that's the magic of decoupling. I decouple the restriction that if I change the hardware, I need to change the software. In this case, I change the hardware. I make sure that the ISA, the assembly language, looks the same. Compiler should still work with whatever programming language you used earlier, right? Now we discover one magic that I want to talk about today. How can we have as many languages as we want? And at the end of the day, compiler becomes the translator for our machine language. That's it, right? How CPU runs the program. Forget about the diagram. I just want to kind of flash this to make sure that, hey, they're hardware. They're hardware. Did you have the code? I'll also want to flash this because just want to show that these are just ones and zero binary, which actually you can represent in assembly language. So here is the assembly code that represents a program. For this program, what it does is add literally doing this 0 plus 5 return 5. That's it. But here, when you have this assembly language, what actually happens when you run this program is the hardware, the first thing it has to do is like, where is my first line? Think about it this way. Computer is dumb. It is stupid. You need to tell them what to do. All right. So the first thing you need to do is that's the first line. The first line, run that. All right. So the first step is fetch. That's the line in assembly that you want to run. Now that you fetch, you know where that line is, you decode. Okay, what does that line do? In this case, push RBP. So decode means that I now know what am I supposed to do. The next step is now that I know what am I supposed to do, perform that action. Somehow we call this execute. So I perform the action. Then if I didn't have to go to the memory, I do it in the memory stage. So if I have to handle things that have to access DRAM, I can do it now. And then the last step, wrapping things up. If I need to update or store result of my instructions,ฮัลโหลทุกคนบ้านไฟตกแป๊บ ขอโทษทีเดี๋ยวกำลังกลับมาอยู่ Sorry, power outage. Be right back. Trying to boot up my desktop again. So let's do a 5 minutes break. I want to just recover from the power outage. All right. I'll be back in 2 or 3 minutes. Now I think my Wi-Fi system is rebooting, so I should be back in 2 or 3 minutes. Okay. So let's do a 5 minutes break. Thank you. Hello, test. Okay. I think I'm back. Can you guys hear me? All right. I don't know what's up with the power delivery here. It's kind of annoying. The past like week it happened twice already. Wait, wrong slide. All right, so let's resume our lecture. Again, we have the assembly code here, right? And I said the first step is to find the line that you're running. So that's called fetch. You go to find the line that you're running right now. Then you decode. Basically, it means that I want to make sure, right? I want to make sure that I know what is the action that I have to do. Then the next step is execute. Execute means that now I know what do I have to do. I run that. Memory means that if I had to go and access DRAM or anything, I would do it now. And then I wrap it up by now that I have the result of my instruction, I want to store the results. Then I move to the next line. If I have the ability to perform the action on this line and the ability to move to the next line, I'm good. That's it. Right? That's it. Now your CPU can run a program. It will keep running until you are at the end of every single line, then you are done. It go back to the OS come back, take control, keep operating your computer, wait until you run the next program. So complicated is this fetch, decode, execute, memory, write back is now expanding into like 30 something stages that all do a bunch of different things. But if you want to zoom into the basic of the CPU, you might heard about cache, right? So you have the cache for your program, you have the decoder, you have the ALU, you have the load store unit that handle the memory accesses, you have to do the write back phase, and then you have things like branch predictor to try to predict, are you going to do the if or the else block? You have the instruction scheduling logic to make sure it can run as fast as possible. You have the future file, you have the SRAM cache, you have the architectural register file. These things will eventually learn what they are, all right? We're gonna eventually learn this component and see why these make your computer fast. So the overall goal of having these components is to make sure that we have a really high single thread performance. I can do one thing really, really, really quickly. All right, so that's the basis of the CPU design. There's also the latency versus throughput question. Latency is how fast can I finish one line of this assembly. Throughput means that, well, what's the time? Even a unit of time, like 1 second, how many things can I finish? Right? So the throughput is how many instructions can I finish given a time frame, like 1 second or 1 millisecond. These are different measurements. I would like to compare this to networking concept between network latency and network bandwidth. Network latency is more like if I send a package to the destination, the latency is the time it takes for me to carry that, well, for some entity to carry that package to the destination. That's the unit of time. Bandwidth means that if I measure 1 second, between these connections, how many bytes of data can I send over, right? Again, they're different. I can send over 1 terabyte of data in 1 second, but have a really bad latency. It can take 1 minute to send one thing over, but I can send billions of billions and billions of things at the same time. It will have a really high bandwidth and really high latency. I can also have a low bandwidth, low latency, which is every single thing I send take maybe 1 nanosecond, but I can only send one thing at a time, right? So if you know architecture, there are obvious real-world examples you can do well. For example, you can do things that are called block matrix multiply. Blocks matrix multiply is making sure that when you do a matrix multiply, A multiplied by B, you slice this up into a smaller block and you do a smaller unit at a time to make sure that everything fits within the cache. Now, let's say you have an application that say, I use a lot of matrix multiply. Well, maybe we can do this in parallel because matrix multiply, if you want to do A multiplied by B, right? If A is a matrix, B is this matrix, I can do all this multiply at once. There's no ordering that I have to be concerned. I can do all the multiply at once. Then once I have the result, I add them together. So I can do this quickly in parallel, maybe on a GPU, right? In fact, the reason why machine learning has seen the light of day, and I'll use that word actually, it has seen the light of day and become reality, it's become possible because it's the advances in hardware. We have a better GPU, we have a better CPU, we have a better hardware to run this really compute intensive machine learning workload that are really useful actually. So GPU in the modern system, you look at this, right? I can buy graphic cards. Over here is a 2080 Ti, relatively old now. And then if I had this thing, I can buy and play games. I can fight tyranny in Far Cry 6. I can relive my I guess my high school day playing Final Fantasy VII Remake. Or if I want to hurt myself through some pain of repeatedly fighting the same boss over and over and over and fail to fight and kill the boss, I can buy Elden Ring. So these are the things I can do with GPU. And for you guys, you've heard by now that GPU can also run any general purpose application through CUDA, right? So now you can run a lot of domain-specific application, machine learning, visual processing, linear algebra, and math algorithm on the GPU, and they're really, really, really fast. It's just because if you know how the GPU works, you would then realize that, hey, maybe making sure there's a language and library and runtime support for running any program, not just graphic application through DirectX or OpenCL. I mean, OpenGL, my bad, OpenGL and DirectX. I can do useful things. Well, I'm not saying gaming are not useful. Gaming is awesome. I love gaming, all right? But you can also do machine learning, AI, scientific application, and a lot of other useful things on the GPU. But again, you cannot just simply run every single thing on a GPU. GPU can be slow too because they have a design trade-off, right? So let's say you have an A100 GPU. It's a really, really powerful machine. But you need to know the hardware. And if you do not understand how the hardware works, to make sure you write a program that run well on a GPU is going to be a really, really hard task. Because at the end of the day, you have to parallelize your program. You have to make sure they contain the same operation over and over and over. Otherwise, it's not going to be fast. Otherwise, actually, be a lot slower than running your program on the CPU. Right? Other example includes things like security. There's a paper in 2018 called the Spectre and the Meltdown attacks. The Spectre and Meltdown attack basically kind of uncover some hardware optimization we've been doing for the past, like, say, 20 years, expose security information that we're not supposed to do. And the attack show how we can write basically a simple program to extract the secret key inside the hardware through the attack called side channel attack. Side channel attacks are attacks where you basically can run an attacker and listen to what's happening on the victim. So let's say I have a legit victim program running on your computer. I can then launch another program to attack this and extract secret through meltdown and Spectre attack. Fun fact, Intel stock, I think, dropped 10% that week. It's been recovered. It's been, to be honest, patched. After the patch, it actually makes the computer a little bit slower because of the certain things you have to do in hardware. But now knowing the hardware, you can do also sketchy thing like attacking a computer or patching, making sure your computer is more secure, right? This is basically another attack discovered by my good friend. His name is Yoongu Kim. This is basically a paper back in I think the articles here is 2019. The paper is actually way more than that. It's called Rowhammer paper. This is basically attack we discovered in the lab that I was with in CMU, my PhD lab. What happened is we discovered I can change the data of someone else's program by just running certain things in assembly, by keep reading and making sure DRAM read this row of data. And because of how physics work, it can flip this row. So I'm trying to access my own data here. And this is someone else's data. But because I keep accessing this data, my data here flip. Because it's a Rowhammer attack, it's actually been a lot. That's actually quite a lot of literature that come after this paper on how to solve this problem, because it's actually not easy to solve using traditional method without a lot of overhead on performance or a lot of overhead to DRAM. So these are some examples of what can happen to the hardware. If you know more about the hardware, there's security problem and security patches that you have to be careful about. Another example, you can build a hardware for certain applications. So I'll use a genome sequence analysis as an example application. So this is critical for a lot of things like personalized medicine or outbreak tracing or evolutionary studies. So what is done is you have the lab samples from, say, the patients or the virus or whatever you want to do the sequencing on. You put the sample in the wet lab onto the machine. The machine would extract part of it's extract the whole genome. Genome is like, if you think of ACTG, your base, the protein, right? It connects your as a human, you have like a genome that defines you, right? That is the DNA sequence. And the sequence, when the machine extracts, it cannot extract the entire thing. You can't get the entire genome at once. It spits out just a fraction of your original DNA sequence, just a fraction of the sequence. We call this a read. So when you go through machine, your genome, when you try to do DNA sequencing, you just get a fraction of them. Your job the next step is, now I have a bunch of fractions together. I can then map them back. We call this read mapping. Read mapping means that I have a reference genome. I know that this is the genome of a human. Every single human in the world is going to be only 3 to 5% different from this. So I can use this as a reference. I map the read back to the original location and then assume that there'll be some mutation. All right. So I can align this read back to the original location. For each matching location, I try to find a similarity, which is the alignment score. Hopefully, alignment score should be pretty similar. It means that this fraction belongs here, right? And it turns out we can do something like approximate string matching. It's an algorithm that we use for search, keyword search. Same algorithm, we can use it for DNA sequencing as well, right? And with this workload, right, you basically take a lot of these reads from the storage, your SSD and hard drive, put that on the CPU and run them. But here's the problem. to do this well, right, it consumes a lot of CPU power. I mean, not power as in electric power, but CPU compute unit. It demands a lot of compute power. Then it also has a lot of data movement. I need to move the data from storage to main memory back to the CPU, right? So many traditional solutions propose things like I can modify the CPU, the cache, the memory so that they become a special hardware just for DNA sequencing or just for read mapping, for example. This kind of helped with the computation overhead, right? So this is like architectural solution. I rebuilt the hardware just for this workload so that they are really fast, right? Also, if you look at this, there's still data movement from SSD all the way to the CPU or accelerator now. Now we call this accelerators. These are not the CPU. It's only run DNA sequencing. Another thing we can figure out is like, hey, there's a lot of things you bring over from the SSD, but you don't need all of them. Why don't you do some filtering in SSD? It's called compute in SSD to make sure that you do the filtering and only bring in what you need. And it turns out the things you need is actually quite small compared to the whole thing, because you don't have to bring in the exact match. Because if it's an exact match, you know the location, you don't have to bring it into the CPU. Or non-matching. Non-matching is like, oh, the potential location probably is not there. Don't bring them in, right? And with this, there's a paper we published called GenStore in last year as well as 2022. Basically, look into like, okay, can we do some in-storage processing to get rid of this data movement overhead? And it turns out we can. And it actually really, really fast, right? Compared to the best accelerator designs, we get about 40% over. Compared to the GPU or CPU solution that are the best on a software solution, we get like 33x over. And it also reduces a lot of energy consumption, which means that the whole design is much more portable. By portable is actually quite important for these kind of workload, because you want to be able to make sure that you can do sequencing everywhere, not just a big hospital, right? Because sequencing workload is actually time critical. If I have a patient in a local hospital dying, and it can help, let's say he or she, with the sequencing data, and having the machine at this local hospital can help as well, right? So as you can see, these things kind of demand really, really state-of-the-art technology that is still evolving. And there's a lot of hardware research into this area as well. More reason, well, advance in hardware can enable new technology. Modern things like Tensor Core, Tensor Processing Unit, or GPU is one example of that. A lot of new hardware design for IoT. I'm not talking about the bullcrap IoT topics that we talk about in Thailand. I'm talking about like actual, like legit. Let's assume there's a lot of different devices. They stress out the network. How do I accelerate them? How do I make sure the load distribution between the compute and all this node bandwidth is done properly? Or even things like, how do I design a language for these IoT devices, right? It's not clear. There's still a lot of research topic going on. Or even things like I want to run cool graphic video or games, right? Actually, we have a lot of high demand for people who know computer architecture and system well. In the world, to be honest, if you know computer system and you have architecture background, there's a lot of job in the world that would to be honest, happily hire you because you know the system, right? Because a lot of programming has close to zero knowledge on how computer actually works. And if this allows you to optimize your code quite well, you can understand what's the performance bottleneck, you can scale your program, hopefully to handle more clients or more workload, right? I said in the world, to be honest, a sad fact, there's not a lot of job that requires architecture background in Thailand, but think big, all right? I mean, it's okay to work abroad. As far as I understand, this is actually a lot of your dream. A lot of the many people's dream to like work at a top tech company, right? You can still further optimize popular workload beyond what most people can because you know the hardware. Even more reason is so that we stop launching crap like this example or this example that why or this example, right? You've seen a lot of this where you like launch some guy want to launch an app and say, hey, we didn't kind of test the scalability and it crashed, right? That as well, like 2,000 transactions per second. Is that good? Well, no. Uh, um, so the people stop suffering from the system when they're down due to some bad design decision, right? Kind of like my message. We want more people who know the system. We want more people who know the hardware. We want more people who know how to scale things up. And we want more solution than just let's throw money into this company so they can come up with a solution for us. Maybe we want to invent our solution. All right. So another quick break. Again, I think I'm good at timing. It's right around 11 o'clock. So we do a 10 minutes break. But intermission, I want to talk about this talk by Eric Lander, The Miracle Machine. This is a really, really powerful talk, at least to me. It actually reflects on a lot of research agenda, how government should fund research, and also how research can make impact to humanity. Because to be honest, a lot of things you do, you might feel like, hey, am I making any impact at all, right? With my research, it seems small. Somehow it does, somehow it does not. It it also depends on whether you can actually extract the true value eventually of certain research as well. So this is your review number 0. This count as your 3% review. So to be honest, this becomes like your extra credit. I would like everyone to go through the video, give some reflection after you listen to the video, and we'll talk about that. All right. So I'll stop the recording for the second session. We'll continue on at 11:10 for the third session, and we'll wrap up with ISA. All right.